So protocols and models. So you probably heard of the term protocols before, like TCP/IP is a protocol. So was Apple Talk, so was IPX, SPX, NetBuoy, so many of them. But protocols are rules or how to do things in IT. Okay, the TCP/IP has set a standard of rules that we all need to obey and be able to, in order to be able to communicate. It's like a language. In this class, we all agreed to speak English, so we can all understand each other. But if I started speaking Chinese, I'm sure some of you guys wouldn't understand me. And even the Chinese people in here probably wouldn't understand me properly because my Chinese is pretty bad. But basically, you have to agree to rules so everyone understands everyone. Computers. So communication fundamentals. Network can vary in size, complexity. It is not enough to just have a connection. You must agree on how to communicate. You need to agree who's the sender, who's the receiver, what type of media you're going to have, how much information do I give you at a go, what order the information should come to you, how do you put it back in the right order. So just imagine, I started talking like this and really, really fast, and now I said everything so fast that I already talk pretty fast, but if I kept on talking fast, it wouldn't make much sense, would it? So we have to agree that we need to talk in a certain rate. I gauge this as a human being because I look at you guys and I look at your eyes and see if you can understand me. If I see you don't understand me, then maybe I'll say differently, or maybe I'll emphasize some words and stuff like that. But that's all protocols. Communication protocols are governed by, so all communications are governed by protocols. Protocols are the rules that we all obey, and these are rules allow for the exchange of information. So rule establishment, individuals must establish a rule or agreement to govern the conversation. Like we said, we agree that this class is conducted in English. We agree that this class is conducted face-to-face. We do have some online people, but we've all agreed to that. And obviously, here's an example. Human communication between governed rules is very difficult. So you notice that first one's very hard to read, isn't it? Because there should be spaces here, but there's no space. So therefore, this is not obeying the rules. But if we actually obey the rules, it becomes very easy to read. It makes sense. So that's just an example. So with the message, the rules govern the encoding, the format, the encapsulation, the size, the timing, and the delivery options. Remember how I said, how much information do I give you in one go? How fast do I talk? And how do I deliver it? Do I deliver it as a visual by doing a demo? Or do I just tell you with words? Do I go to the practical thing? Do I decide that you can learn the commands better by practicing yourself? These are what humans do all the time, but computers and devices must also decide this. And that's where protocol goes. Message encoding is the process of converting information to another acceptable form of for transmission. Data decoding is the reverse of that. So before we send a file, we encode it. When it gets to the receiver, they decode it, okay, to get back the original information. Message formatting is very important because if we look at a letter, we all know that you must put the recipient and the address in the middle. You must put a stamp over there. And in Australia, we got our postcode on the bottom right. Trust me, if you write that envelope in a different way, you'll never get to that location because the post office can't handle it. So basically, these are the rules again. So in a TCP/IP packet, for example, there's what's called a header. Okay, before your actual content of your message, there's a header, which actually is like the envelope with all the addressing information, the sender information, all those kind of things. So we've got a payload length. Oh, how big is this letter? The hop limit. How many routers can I go through before this message expires? It's just like if you had a letter that keeps on going from post office to post office, but never being able to find a destination, eventually they're going to chuck the letter out, aren't they? And then we've got the source IP address, who's it from, computer, who's it from, destination IP address. Where's it going? The message size, like if I have a super duper computer and a fast network, I could probably send a lot of information in one go, in one giant packet. But if this computer can't accept all that information in one go, then it's pointless. And or if this is too big for every network in between to carry, then it's pointless. So they must agree to a message size, and instead of it as one big giant envelope, you could split it up into 3 letters. Encoding between hosts must be an appropriate format for the medium. Messages are sent across the network and converted into bits. Bits are the ones and zeros, if you don't understand that. And the bits are encoded in patterns of light, sound, or electrical impulses. The destination host must be able to interpret these signals. Okay, there's no point me using fiber and this computer not capable of fiber on the other side. Message timing and flow control. Flow control manages the rate of data transmission. How fast am I talking? The response time, if I say something and I ask you a question, like before when I ask a question, I look around the room. I don't just wait forever. I start looking. Gets a bit awkward after a while, doesn't it? And then we say something or I say something. So, but the response timeout. So if the sender who I'm sending this message at is not responding in a timely manner, maybe they've never got my message. Maybe I have to repeat myself to the students, for example. Maybe I have to resend it. Access methods determines when someone can send a message. There are many. There may be various rules governing issues like collisions. Okay, in old days, this is more a thing in old days when we use hubs. Only one computer can talk at a time. These days, we've got switches, so all of them can talk and listen at the same time. But if you want to think about what a collision is, we've got a pass. We've got what's called a shared medium, the air. We're using sound. If I'm talking now, and I'm the only one talking, you guys can hear me pretty clearly, can't you? But just imagine if we all started talking at the same time. Could you pick out what I'm saying clearly? Probably not. So that's like what a collision is. If all the computers are using the same media and they're all talking at the same time, so I'll give you an example of Wi-Fi. If Wi-Fi uses the same medium, radio frequencies, okay, assuming you're on the same channel, you're all going to be using the same radio frequencies. And if all of you guys start broadcasting or sending messages at that point in time, then it's not going to get through. All right, so message delivery options. So there's unicast, multicast, and broadcast. So what was your name? Matthew. So you notice that I was talking to one person, Matthew. That's what's called a unicast, one-to-one. Hey, people on this side of the room, can you pay attention quickly? Just look at me right now. That's what's called multicast. Instead of talking to one person, I'm talking to a group of people. Not everyone, but a group of people. That's what's called multicast. Well, obviously, we're talking about computers here, not people. But broadcast is what I'm doing right now. I'm saying it once, but all of you guys are hearing my message. And you're all trying to ingest it or understand it. So protocols are the rules. And network protocols defines a common set of rules. And they include the software, hardware, or both. Protocols must have their own function, format, and rules. Okay, let's have a look at this example. Devices must agree upon the protocol to communicate. Protocols may have one or more functions. So protocol may have one function. Sorry, that doesn't make sense, does it? Someone's not using the right protocols there. So, as in may have more than one function, should I say? So this protocol has functions of addressing, source and destination IP addresses, reliability. Well, reliability means you're ensuring your message gets there. How do I know you can understand me, Matthew? I would probably ask, Matthew, did you hear what I just said? That's just checking, isn't it? So basically, if we have reliability, I might ask for a feedback, confirmation that you've received the message. Okay? There's flow control, like I said, the speed. We agree, we control the flow to suit both of us. There's no point in me talking really fast and you not understanding. Error detection, what if I say something Oh, sorry. What if I send you something, but when you got it, it's all scrambled up. It's corrupted. How do you know it's corrupted? It's all ones and zeros at the end of the day, isn't it? How do you know it's correct or not correct if it's ones and zeros? Well, there must be something built in to check if the message is still correct. So there's usually what's called a CRC, cyclical redundancy check. So if I did a hash on this number, on the ones and zeros, I should get this answer when I sent it. But when you get it, you do the same hash or the algorithm, do you get the same number answer? If you do, then everything's fine. But if you don't, then something's gone miss in this message. If I say to you, there should be 25 words in my message, and when you get it, you're going to get 24 words, and obviously something's gone wrong, hasn't it? So basically that's what it's trying to do. And there's an application interface which process communication between network applications. Okay, protocol interactions. So if we look at this, this is the layers. There's a layers. So in networking or in communication, there's different protocol layers. So there's Ethernet right at the bottom. This delivers NIC messages from one NIC to another NIC, and we use what's called a physical address or MAC address. Okay, and this is only inside the LAN. So if I'm communicating with Google, I will use MAC addresses between my computer to get to my gateway, because that's one LAN. Then I would use the IP addresses to actually get to the destination, even if they're global. No one really thinks about MAC addresses because no one cares about it really. That you just have MAC addresses. As long as you don't have duplicate MAC addresses, then you're fine. Or until you need to do some sort of MAC address filtering, you're fine. The IP address is probably more important because that's the ones that you do configure in a DHCP. You do ping and stuff like that. But MAC addresses are there for basically layer two communication and addressing. And we'll talk about the different layers of the OSI later. Layer 2 means just the second layer from the bottom. There's the transmission control or TCP layer, and this is where your error checking, guarantee of delivery, and flow control happens. And then there's the application layer, which in this case, in this example, it's a HTTP. Anyone know what that means? What's HTTP? Yeah, hypertext transfer protocol, right there. But what is that associated with? What kind of things do you associate? Well, actual website, correct? Website, accessing a website, HTTP or HTTPS. So I can tell you that this connection is talking about this computer accessing a web server here because it's using that HTTP protocol. So protocol suites. So we've got the TCP/IP protocol suites. It's got these layers: network access layer, internet layer, transport layer, and application layer. So that's 4 layers of a TCP/IP protocol suite. And these are some of the protocols that we can use at each of the layers. And we'll talk more about this in the future. But you know what? Hint, hint, tip, tip. In your assignment 1, you probably may have something like this that you have to fill out. Okay, just keep that in the back of your mind. Yeah, so basically, let's go. So from this web client to this web server, we are sending a traffic. Okay, you can see that there's an Ethernet, there's IP, there's TCP, and there's data, and there's the Ethernet frame. So each one of these areas is a different layer. So it's, if you like to think of it, you got your data, the actual information you want to send. Then we wrap it up into a TCP segment. That's one type of envelope. Then we wrap that envelope into an IP packet. And then we put that envelope into an Ethernet frame. because don't forget, this Ethernet is used for local area connection. When it gets here, it strips away or decapsulates, works out the IP address. Is it my IP address? Yes. And it will keep on decapsulating, and then it will eventually read the data. But when it's actually being sent on the physical media, it's actually all ones and zeros, like blinking lights or on and off, stuff like that. Standards Organizations International, or the OSI, has various other areas, but the OSI is probably one of the biggest. Let's keep on going. These ones are not very interesting. So we have the OSI model, the Organisation Standards International, like I was saying, it's a French place, or International Standards Organization if you want to put it in English. So everything we do in IT and network communication obeys the model. So these are theoretical models to help us design protocols and allow for communication. Each layer is independent of every other layer, but they all must fit together. What does that mean? That means if we talk about physical layer, we spoke about how we can have Ethernet, which is using the copper cables. We can use fiber optics. We can use the radio frequencies. We can use satellite, all sorts of different media, couldn't we? So that's why this layer is independent from every other layer, because we can take any physical connection and substitute it in. Okay, I'm on my Wi-Fi. I'm using radio frequency. We just use substitute the physical layer for Wi-Fi. The data link layer is the frames. The network layer is the IP addressing. The transport layer is the different ports. Like you might have heard that, remember we talked about port HTTP before? That's port 80, if you remember. You know those ports, we sort of, on our firewalls, we spoke about that earlier, we open and close those ports to allow or deny traffic through the firewall. And then we have the application layer, which is your different protocols and applications that you use. But if you look at this is the OSI layer. It's got 7 layers. And this is the TCP/IP layer. Again, your Simon 1 has something that's looks just like this almost, just as a tip. And there's 4 layers, but they sort of match up. There's equivalencies. And how do you remember this? In the Cisco exam, you definitely have to remember the layers. I remember by Phil Donahue never televised sick people anymore. Anyone know who Phil Donahue is? He used to be a daytime talk show host when I was a kid. And basically, Phil Donahue never televised sick people anymore. There's many, many others, not just mine. That's the one I use. But let's see if we can find some other ones. All right, so let's OSI models saying all people seem to need data processing. That goes from top to bottom, and there's many others. Okay, Henry mnemonics. It talks about it, but you can get your own. But that's the one I use about Phil Donahue. All right, so there are benefits of using this layered model because you can substitute a different type at each layer. It's not vendor specific. Just because I'm Cisco, you're Microsoft, and you're Novell, for example, it doesn't mean we can't all use the same protocols. I will just substitute my version of this in this layer as long as it meets the rules. Then it'll work with your version. That's a beauty of having standards. Like, for example, if we have I'll tell you something about that my lecturer used to tell me. When they first settled Australia, they had railways to connect Australia up. But the problem is that some states will have their own standards and other states will have different standards. And when they wanted to connect the railways to the different states, they just didn't fit. So some were using the wide gauge, some were using narrow gauge, and then when they met at the state borders, they just couldn't connect. That's lack of standards. But when you have the same standards, as long as you're building it to the ISO 35 standard or something like that, and I'm building it to the ISO 35 standard, wherever that might be, then we know that when we put them together, they'll interoperate. And that's the IT thing. So how many different apps have you seen in your life on your phone, on your computers? How many different vendors of operating systems? How many hardware vendors? And how many different hardware devices? They all seem to work with each other, don't they? And that's because across the board, we're using these standards. And in the past, in the bad old days, probably sometimes now you might even see it, there's a proprietary standard. Like, for example, Apple with their App Store. Unless you pay Apple money to be in the App Store, you can't actually publish your apps. Whereas if you use Android, you can actually just get the, I forgot the file for APK files. You can just install it into your phone. It's dangerous also, but it's possible. Okay, so in the past, you had proprietary standards. Like, for example, like I said, there was a protocol called Apple Talk. And guess which operating system was using that? And obviously that's a Mac, and no one else was. Fine between Macs, but how do you communicate with each other? So these are the different models, and like I said, there'll be questions in your first assignment regarding these. So look at these slides or the references and see how the TCP/IP and the OSI models sort of interact. Like I said, there was a one where you had the different protocols and stuff, and the different elements in there.